When complexity learns to grow, based on Chapter 6 of George Kampis's Self-Modifying Systems in Biology and Cognitive Science, 1991. If a system can modify itself, can it also grow its own complexity? Not just accumulate change, but deepen, evolve, surprise? Welcome to DeepVisus. In this episode, we enter Chapter 6, a pivotal moment in George Kampis's exploration, where his theory of component systems comes alive. It's no longer just about escaping the limits of classical dynamics. Now, it's about understanding how real systems, biological, cognitive, living, can grow more complex from within. Let's follow the path of that growth. Basic concepts of complexity. Kampis begins with a question science has long struggled to pin down. What is complexity really? It's not just about size. It's not just the number of parts. He walks us through early attempts, algorithmic information theory, entropy, even statistical definitions. Each tries to formalize how much structure a system has. But Kampis finds a flaw. Most of these measures assume the system is fixed, that the rules are external, and the boundaries already drawn. And that's exactly the opposite of how life behaves. Transformational versus constructive dynamics. Here, the heartbeat of the chapter begins. Kampis draws a sharp distinction. Transformational systems. The rules are fixed, and everything evolves by rearranging existing elements. Like a Rubik's Cube, you can twist endlessly, but you'll never get a new face. Constructive systems. These systems generate new components, change their own rules, and open new dimensions. A caterpillar becomes a butterfly. A brain learns to imagine. These are not transformations. They are emergences. They are constructions. Component systems and the construction of complexity. Now Kampis brings in the star of his framework, the component system. This is no ordinary machine. It doesn't just run, it builds. Each part of the system is a component that can interact, replicate, create new types of components, and permanently alter the system's structure. As these interactions stack and echo, the system begins to grow not just in scale, but in dimensionality. It becomes a complexity-generating process. Think of an evolving ecosystem, or a developing mind, where each step opens new paths never available before. Self-modification and irreversibility. In classical models, you can rewind the tape. In Kampis's world, you can't. Component systems are irreversible. Why? Because when you add a new component that changes the rules, you haven't just changed the state. You've changed what counts as possible. This is real creativity, not simulated novelty. And once it happens, there's no going back. This is why complexity, in such systems, is not just a measurement. It's a direction. A vector, not a statistic. A new paradigm of biological modeling. Finally, Kampis brings it home. He tells us, if we want to model real systems, living, evolving, thinking systems, we must let go of static models. We must stop thinking in frozen equations. Instead, we need systems that construct themselves, that generate information through interaction, and that grow their own future. This is not just a new tool. It's a new paradigm. A new way of thinking about life, mind, and science itself. Conclusion: complexity isn't a thing, it's a becoming. So let's return to our opening question. If a system can modify itself, can it grow its own complexity? Kampis answers, yes, if it can build its own rules. And once it can do that, it's no longer a passive subject of laws. It becomes an agent of emergence, a system that doesn't just change, but becomes more than it was. This is what complexity truly means in a living world. In our next episode, we'll follow this idea even further, into the nature of information itself. What is information in a world where the system creates meaning from the inside out. Until then, stay sharp, stay curious, and remember, DeepVisus, where vision meets depth.